Imagine for a second that you are trying to move efficiently through water, but the only tool you have to propel yourself is a spinning fan.
Sounds pretty exhausting.
Right. I mean, you have to constantly churn the fluid. You're basically fighting the water just to maintain your forward momentum.
Yeah, it's a highly inefficient way to spend your finite energy. You are literally fighting the medium you are trying to traverse.
And yet that is essentially how marine propulsion has worked for over a century. We just, spin things faster and hope for the best.
Exactly.
So today we are doing a deep dive into a groundbreaking concept paper that challenges that exact premise. We're looking at a highly technical document titled N5 Prop, Phase-Structured Marine Propulsion.
And we should establish right up front who wrote this.
Yes, it was authored by Levinay Moten, PhD, and his organization, N5 Digital, Inc.
Right. And the context of the source material is crucial. This was prepared specifically for the Office of Naval Research, the ONR.
Oh, wow. So this isn't for, like, a weekend fishing boat.
No, not at all. So if you are listening to this, understand that we are not talking about a new motor for a consumer speedboat. This is the bleeding edge of defense research. It's designed to solve problems on a tactical global scale.
That is wild. Our mission for this deep dive is to explore how moving away from that century-old method, the spinning propeller, and moving toward a radically different linear stroke system could completely redefine underwater technology.
It really could.
We're talking autonomous drones, modern naval warfare, and maybe even aerial flight.
What's fascinating here is the core thesis of Dr. Moten's paper. The future of propulsion is not in spinning a blade faster, but in interacting with the fluid smarter.
Smarter, not harder.
Precisely. It is about fundamentally rethinking how a machine talks to the water around it rather than just brute forcing its way through.
Okay, let's unpack this.
Yeah.
Because before we can understand this futuristic N5 prop solution, we really need to look at why the Navy is desperately searching for an alternative to traditional propellers in the first place.
The inherent flaws.
Yeah, exactly. I was reading through the source, and I realized a good way to visualize the flaw in our current technology. Using a traditional propeller is a bit like trying to run on an icy surface while wearing entirely smooth shoes.
That's a great image.
Right. You might inch forward, but you waste a massive amount of energy just slipping and churning up the ice beneath you.
That is a much more accurate way to visualize it than most people realize. To ground your ice analogy in the physics outlined in the paper, rotating blades are inherently inefficient because they are a compromised design.
Compromised how?
Well, they are simultaneously attempting two conflicting actions within the exact same mechanical motion.
Let me guess. They're trying to slice forward into the water while at the exact same time trying to push a massive volume of water backward to create thrust.
That is the core conflict, yes.
Yeah.
Those two actions are physically coupled in a rotary system. The blade has to move forward against the heavy resistance of the water before its angled pitch can even begin to contribute to forward propulsion.
Oh, I see.
So you have a persistent, continuous drag component that is just intrinsic to the operation of the system. You are literally constantly working against yourself.
Which means a staggering loss of energy.
Yeah.
But I have to ask the obvious question here. I mean, if this spinning blade design is so deeply flawed and wasteful, why on earth has it been the undisputed global standard for over 100 years?
Because for most of the 20th century, we solved the inefficiency problem with sheer brute force.
Just bigger engines.
Exactly. If your propeller is wasting energy, you just attach it to a massive diesel engine or a nuclear reactor that can afford to burn excess fuel. You just overpower the inefficiency.
That makes sense.
But the text details why that era is ending. It breaks down the specific mechanisms of this wasted energy. Beyond just the continuous drag, you have the creation of rotational flow.
Like swirling water.
Right. A spinning propeller imparts angular momentum to the water. It creates these expanding, turbulent vortex structures.
Yeah, it looks like a watery tornado coming off the back of a boat.
A watery tornado is exactly what it is, and swirling flows and turbulence do absolutely nothing to push a vehicle forward. It is just raw energy dissipated into the environment as heat and chaotic motion.
So if you are listening to this and you've ever wondered why underwater drones, or honestly even your consumer electronic water gadgets suffer from such incredibly limited battery life, this is the primary culprit.
It absolutely is.
You don't have a massive diesel engine to compensate. You are draining a tiny battery just to swirl the water around in circles.
And in modern autonomous defense systems, where energy availability is strictly limited by the size of the drone, that inefficiency directly caps your entire mission capability.
Wow.
Every joule of energy spent creating a turbulent vortex is a joule not spent extending your operational range.
Which brings us to the paradigm shift.
Yeah.
N5 Digital proposes solving this massive energy leak by completely separating the thrust and the recovery into two distinct phases.
Right, breaking them apart.
And they introduce a concept that plays a huge role in this paper, anisotropy.
Anisotropy is a critical concept here. In its most general scientific sense, it refers to the directional dependence of a physical interaction.
Meaning the way something interacts with its environment changes depending on the direction it happens to be moving.
Correct.
The paper points to natural analogies for this, like the way fish or shark skin interact with water.
Yes, biological systems are absolute masters of anisotropy. A fish doesn't move forward through the brute force of a spinning blade. It uses subtle, directionally structured interactions.
Which is way more elegant.
Very elegant. The microscopic arrangement of its scales, the specific structural features on a shark skin, these create a preferential response in the fluid. Moving in one direction produces a smooth, low-friction glide, while moving in the opposite direction creates significant resistance to push off against.
I have to stop you there, though. I was looking at this comparison to a fish in the source material, and frankly, I was a little skeptical.
Oh, why is that?
Well, a machine is essentially a rigid tube of metal and composites. It doesn't have muscles, tendons, or a flexible spine. How does a rigid machine actually mimic the subtle, asymmetric movements of a fish without just flopping around uselessly? You can't just build a metal fish.
That is a very valid point, and the paper addresses it. If we connect this to the bigger picture, Dr. Moten is not proposing we mimic the biological form of the fish.
Oh, so we aren't building a robotic spine.
No, not at all. We are mimicking the physical principles of its movement. He calls this phase-structured interaction. And rather than a flexible body, it breaks down into two highly engineered, distinct mechanical phases.
Okay, let's walk through those. There's the propulsion phase and then the reset phase. What is actually happening physically during the propulsion phase?
During the propulsion phase, the N5 prop's propeller physically reconfigures. It closes up to present a high-resistance surface to the water.
So if you're picturing a standard boat motor right now with fixed blades, you need to completely throw that image out of your head. This propeller essentially transforms into a solid wall.
That is a great way to picture it. It establishes maximum coupling with the fluid. It grabs a coherent, solid volume of water and accelerates it directly backward.
Like pushing off a wall.
Exactly. Think of it like a drag racing tire gripping dry asphalt. There's no slipping. The system transfers its momentum efficiently in a single, directed, powerful impulse.
Okay, pushing a giant wall of water backwards makes perfect sense for generating thrust. But here's the massive mechanical problem. Once that stroke is complete, that propeller has to return to its starting position to push again.
The reset phase.
Yeah. If it drags that exact same wall back through the water, wouldn't it just act like a massive brake and cancel out all the forward motion it just created?
It absolutely would if it stayed a wall. But that's where the structural reconfiguration comes in for the reset phase.
Ah, it changes shape.
During the reset, the propeller structurally opens. It reconfigures into a low-resistance state. Imagine louvers on a window opening up, or an umbrella collapsing.
Oh, wow.
It slips back to its initial position, cutting through the fluid with minimal opposition.
Wait, really? So it's heavily, violently interacting with the water when pushing backward, and then essentially folding up and ignoring the water when pulling forward to reset.
That is the temporal anisotropy in action. The system is strongly coupled to the fluid only when generating thrust and weakly coupled when recovering. The paper dives deep into the formal physics of this, specifically looking at time-dependent momentum transfer.
Yeah, I saw those equations in the source material. Like, it's incredibly dense. They mention integral equations governing the force. Let's try to translate that into English for the listener.
Of course. An integral equation in this context is just a mathematical way of measuring total effort or total force applied over a specific window of time.
Okay.
In a conventional propeller, your thrust is a relatively smooth, continuous function, but it is deeply infected with continuous drag. You are constantly pushing and constantly dragging.
Which is exhausting.
Right. But N5 prop concentrates all the useful impulse into discrete high-force intervals.
Here's where it gets really interesting. To synthesize this, it's the difference between stirring water continuously, where you're just wasting energy into a swirl, versus pushing water in discrete directed pulses.
coherent momentum transfer.
Yes. The math in the paper proves that the force generated during the propulsion phase, which they call F high, is vastly greater than the tiny amount of drag force during the reset phase, or F low.
Exactly. Because the reset phase is so aerodynamically or hydrodynamically invisible, it contributes almost nothing to energy loss.
So all the energy from your battery goes exactly where you want it to go, forward.
And there is a secondary benefit here. Because you aren't physically bound to a fixed rotational cycle of a spinning shaft, the system becomes incredibly adaptable.
Now so.
The timing, the amplitude, the frequency of every single individual stroke can be adjusted dynamically in real time by the drone's computer.
Okay, but pushing a wall of water and snapping back sounds great in theory. This naturally raises a massive engineering question. A standard rotary engine spins in circles. How are they actually driving this jerky, rapid-fire back-and-forth motion?
It's a huge challenge.
If you hook this up to a standard motor, wouldn't it just vibrate itself to pieces?
It absolutely would destroy a conventional motor. That is where the system architecture comes in. And it is just as radical as the folding propeller design. N5 Prop completely abandons rotary motors.
Completely.
There is no spinning engine inside the hull at all.
None. So if we think about a bicycle, instead of pedaling in circles to drive a chain, which is a rotary motion, it's like a piston firing straight back and forth, directly delivering the power. It's a purely linear drive.
Specifically, it is a linear electromagnetic engine. And the mechanical advantages detailed in the text are enormous.
Because it's not mechanical in the traditional sense.
Right. Because it generates linear motion directly through electromagnetic fields pushing and pulling against each other, you eliminate an entire class of physical inefficiencies. There are no drive shafts, there are no gears to strip, there are no complex bearings to lubricate.
Wait, so it's essentially just powerful magnets pulling a rod back and forth inside a tube.
In its most basic conceptual form, yes. It significantly reduces energy losses from mechanical friction. And because the motion is governed entirely by electrical input switching polarities, rather than the mechanical inertia of heavy metal gears, the system responds instantaneously to control signals.
But hold on. If there are no gears, no physical shock absorbers, what happens to the propeller itself? The physical toll of slamming closed, pushing a massive wall of heavy water, snapping open and pulling back over and over again, thousands of times an hour.
It's immense stress.
It seems like the sheer stress would just tear the material apart.
Material science is the absolute linchpin of this entire architecture. If we didn't have modern materials, this engine would be impossible to build. Dr. Nemotin outlines very specific material requirements to survive these rapidly alternating impact loads.
What kind of materials?
The internal engine components rely on ferromagnetic materials.
And for anyone who hasn't taken a physics class recently, ferromagnetic just means materials like iron or specialized alloys that react incredibly powerfully and, more importantly, almost instantly to magnetic fields.
Right. They have to switch states in milliseconds. And for the external propeller itself, the part doing the violent pushing and folding, they require ultralight composite materials.
Because it has to be light to move fast.
Exactly. These composites have incredibly high tensile strength and fatigue resistance. You need a material that has very low physical mass, so the engine can change its direction instantly without fighting its weight. And it also needs the structural resilience of steel to withstand the continuous hammering impact of the high resistance phase against the water.
So let's take a step back and look at the whole picture. We have a system with no gears, no spinning shafts. It pulses rapidly back and forth, folding and unfolding, built out of advanced composites and highly reactive ferromagnetic metals.
It is a marvel of engineering.
It really is. So what does this all mean? Let's connect this back to the original client for this research paper, the Office of Naval Research. If you're sitting there listening to this, imagine the ocean battle space of tomorrow. Why do unmanned underwater vehicles, these autonomous drones, desperately need this?
Because the modern naval battle space is undergoing a massive, terrifying transformation. Above the water, surface ships are becoming increasingly vulnerable to detection and attack from long-range aerial threats and satellite tracking.
Right, there's nowhere to hide on the surface.
Exactly. So the strategic advantage is shifting entirely beneath the waves. The future of naval power relies heavily on stealth, prolonged autonomy, and rapid maneuverability.
It's all about submarines and drone swarms. Let's walk through the 4 major performance leaps outlined in the text that completely change a mission. Imagine a Navy drone infiltrating hostile waters. Its primary objective is simply to survive and remain undetected.
And that is exactly where the N5 prop provides its first major strategic leap: unmatched stealth. Traditional propellers generate continuous broadband noise.
They're loud.
Very. They create cavitation tiny bubbles that collapse loudly, and the rhythmic thumping of blade passage. Enemy sonar is specifically tuned to hear that exact acoustic signature.
But this linear stroke system doesn't spin, it pulses.
Exactly. It produces a completely different acoustic profile. It's lower frequency, lower amplitude. The wake it leaves behind isn't a massive swirling vortex. It is narrow, directionally focused, and dissipates rapidly into the ocean,
Making it invisible to sonar.
It dramatically shrinks the drone's hydrodynamic footprint, making it incredibly difficult, if not impossible, for traditional enemy sonar systems to isolate it from background ocean noise.
Okay, so because the drone is silent, it can hide. It can slip past the sonar nets. But operating deep in enemy territory requires immense battery life, which brings up the second advantage, the massive energy efficiency we discussed earlier.
The energy savings. In a tactical context, less wasted energy translates directly to extended mission durations. It allows that silent drone to penetrate much deeper into contested, hostile environments.
And just wait there.
Right. It can loiter there for weeks, gathering in intelligence or waiting for a high-value target to appear, all without needing to surface, expose itself, or return to a mothership to recharge.
But let's say the worst happens. The drone is finally spotted by an enemy submarine. It needs to survive. And that requires the third leap, which is shedding the rotational inertia that plagues standard vehicles.
Hypermaneuverability. This is where the lack of spinning parts becomes a literal lifesaver. Rotational inertia is the tendency of a spinning object to want to keep spinning.
Like a spinning top.
Think of a heavy spinning top? Yes. It strongly resists any force trying to tip it over or change its direction. A spinning boat propeller does the exact same thing. It physically resists rapid changes in speed and direction.
Because it's a massive chunk of spinning metal that wants to keep going in a circle.
Right. But the N5 prop's linear engine has zero angular momentum. It isn't spinning. The propulsion cycle can be halted entirely, reversed, or modulated in a fraction of a second.
So it can just stop dead.
The drone can execute rapid acceleration, instant deceleration, and violent, sharp directional changes for evasive maneuvers. A traditional drone physically cannot replicate that agility. It would just plow forward while trying to turn.
It can essentially stop on a dime, pivot, and dart away. And if it needs to dart away, it needs to be fast. Which brings us to the final tactical advantage from the text.
High-speed bursts. Because the system efficiently transfers almost all its electrical energy into pure forward motion, and because it can rapidly modulate its thrust without waiting for a propeller to spool up, it is capable of short bursts of extreme cruising speeds.
How fast are we talking?
The paper specifically notes that this linear stroke architecture is capable of speeds on the order of 100 kilometers per hour.
Wait, really? 100 kilometers an hour? Underwater?
Yes.
Pushing through water that dense, that is terrifyingly fast.
It is specifically designed for interception, pursuit, or rapid evasion scenarios. When you string that narrative together, a drone that can arrive entirely undetected, wait silently for weeks on a single charge, instantly dodge an incoming threat, and then escape at 100 kilometers an hour, you completely rewrite the rules of undersea engagement.
I want you to really picture that strategic shift. We are talking about autonomous swarms operating deep in the ocean, completely unseen by traditional surface ships, possessing maneuverability that defies the last 100 years of submarine physics.
It's an incredible leap.
It's no wonder the ONR is funding this kind of conceptual research.
It is a complete paradigm shift from brute force to intelligent interaction.
It really has been quite the journey today. We started by looking at the inherent, century-old flaws of the spinning propeller, the wasted energy, the turbulent vortices, the constant fight against the fluid.
The parachute analogy.
Exactly. And we've walked through Dr. Levne Moten's incredibly elegant solution, a biomimetic linear stroke electromagnetic drive that powerfully pulses through the water, folding and unfolding, rather than just spinning blindly.
This raises an important question, one that the conclusion of the paper touches upon beautifully. This isn't just a clever new engine design. It is a fundamental transition in how humanity conceives of moving through physical media.
That's a profound way to look at it.
Dr. Moten compares it to the profound historical shift we made when we moved from purely mechanical, steam-driven systems to advanced electromagnetic systems. It establishes a completely new baseline for engineering.
And that leads perfectly into a final provocative thought I want to leave you with today. We've spent this entire deep dive underwater. But the source paper briefly mentions that these principles of anisotropy and linear strokes could theoretically be adapted to aerial systems and hybrid environments operating at the boundaries of domains.
That is where it gets truly sci-fi.
Right. Think about the implications of that. If this phase-structured propulsion can overcome the dense, heavy, unforgiving resistance of the ocean without spinning an agent, imagine a future transmedium vehicle.
Moving from air to water.
Yes. Picture a drone that pulses its way silently through the sky, its wings or louvers using these same anisotropic strokes against the air to stay aloft. And then without altering its engine, without shedding any booster rockets or deploying parachutes, it dives seamlessly into the ocean.
Wow.
It just continues to propel itself deep into the water, using the exact same rhythmic, pulsing strokes it used in the clouds. The line between an aircraft and a submarine doesn't just blur, it completely vanishes.
Now that is something to think about.
It really is. Thank you for joining us on this deep dive. Keep questioning the mechanics of the world around you, and we'll see you next time.